Hello, guys. Welcome and thank you for joining us today. We're going to give it a few more minutes just for everyone to log in. Now, while we wait, a little information about Prolim. Now, we are a leading PLM, cloud, Mindex, and digital transformation solution provider with a global footprint and expertise in the latest technologies. Prolim is the partner to speed up your digital transformation journey. All right, guys, we're going to give it just a couple minutes. We will start shortly. Thank you. Let's go ahead and begin our tech talk today on the evolution of reverse engineering. Now, questions will be answered live at the end, but feel free to go ahead and enter them into the chat as you have them. And then again, we'll answer all questions at the end of the tech talk. Now, our presenter today is Aaron. Now, Aaron's in our Cincinnati office, and just a little bit about Aaron. He has over 20 years of experience in the design engineering field, and that includes work in mechanical, environmental, architectural, and automotive. So his design experience has gone from concept design, production development, all the way through to production procurement. And this of course, includes extensive experience using 3D design packages. All right, Aaron, I am excited to hear what you have to say today. So please go ahead. The Tech Talk is now yours.
Thanks for the introduction, Misty. I appreciate it. So hello, and thank you everyone for attending today's Tech Talk. So today we're going to discuss the evolution of reverse engineering. So we'll look at some typical challenges, new functionality to kind of help us overcome some of these challenges. So let's go ahead and get into it. So solid edge mechanical design, always allowing us to click less and do more. So let's see how. So for today's agenda, we're going to look at what is reverse engineering, and we're going to look at why we use reverse engineering. And then we'll look at how reverse engineering is handled inside of Solid Edge. And we'll look at some mesh data editing concepts as well. And then we'll look at some specific Solid Edge reverse engineering tools. And then we'll look at some newly improved reverse engineering methods. So due to the increased popular demand and tremendous growth of additive manufacturing industry, reverse engineering has become an even more vital part of the additive manufacturing process. So from generative design to reverse engineering to additive manufacturing or 3D printing, mesh model and BREP, boundary representation, and convergent hybrid modeling. So these are all kind of new terms that are and functions that are driving this additive manufacturing industry. So what do we mean by reverse engineering? Reverse engineering is the process of taking a physical part and converting it into a workable 3D CAD design for the purposes of duplicating, modifying, or improving a design. So this is now commonly done with the use of affordable, portable 3D perceptron scanners. These provide an accurate representation of the physical part via a mesh model, or an STL. Unfortunately, these scan mesh outputs aren't intelligent and sometimes don't capture all of the elements of the part that are required. So Solid Edge makes this process very easy by continuously enhancing the reverse engineering methods and tools available within the software that will kind of allow us to take this mesh model into a workable 3D solid model. Or now it's kind of a hybrid of the two known as convergent hybrid modeling. And we'll look at this a little later. So it's important to note, though, that the reverse engineering tools that are specific to Solid Edge are only available in the synchronous environment. But they are now included in the classic and premium versions of Solid Edge. So this process is going to provide us an avenue for faster development, quality improvements, production customization, and even cost reduction. So many reasons to have that CAD design model there in your library. So as scanning hardware and software become more affordable and accessible, 3D scans of components have become much more prevalent in the industry. However, because the scan data is usually read using location-based point cloud data, CAD systems need to find a way in which to read in and display this data accurately. That's kind of the challenge. So Solid Edge reverse engineering manages this data once it's been converted to a mesh. So that highlighted area there is where Solid Edge really focuses on this process. So let's take a minute just to kind of educate everyone on the differences between a mesh model and a BREP model, in case maybe you haven't heard the term BREP. So first, what is a mesh? A mesh is a native geometry representation needed in order to display objects in a CAD environment, usually consisting of a collection of vertices or points and faces, which are typically triangles or rectangles, as you can see here on the left-hand side. On the other hand, on the right-hand view, we have a kind of what a BREP is, and that stands for boundary representation. It consists of representing surfaces through mathematical equations and a set of limits in a 3D space. So that BREP are both more compact in their definition while retaining more structural information and integrity of the shape. So with this basic information, let's move on. So here's kind of the evolution of reverse engineering inside of Solid Edge. So in 2016, the reverse engineering specific tools and commands were introduced into Solid Edge, but they only worked with the imported mesh data. And it was only available as an add-on portfolio product, meaning you had to pay extra just to have access to the reverse engineering modules. And then in 2022, further reverse engineering functionality was developed. So we got reference point cloud data visualization was introduced in 22, and this allowed us to bring in scanned environment data. So this is typically used for machine or maybe equipment placement verification of your part or your system. We also had convergent modeling, which was native Solid Edge mesh data that was approved by allowing us to work directly on that mesh itself. And we'll look at an example of this here shortly. And then we were able to export mesh data, that scan data and 3D print files were now accepted. So now we could output these files as 3D print data. We also introduced synchronous move and rotate commands for the mesh body as well. So now we could perform some of the synchronous moves on the mesh body itself. And then in 22 was when Solid Edge introduced this as a included product inside of the premium and classic versions of Solid Edge. So if you're a current user of Solid Edge and you have a premium or classic seat, you have access to this, both the 3D print and the reverse engineering tab inside of the synchronous environment. Then in Solid Edge 2023, the term convergent hybrid modeling was introduced. So this allowed users to combine that mesh data and that BREP data operations in one environment. So basically meaning that you could use both data types simultaneously. And then this year with the latest release of Solid Edge 2024, there was some continued development in the reverse engineering environment. So there were some further improvements for automatic region detection. And then they also added some mesh and boundary smoothing commands. So as you can see, it's continuously being developed and invested in this area for Solid Edge. So let's touch a little on this convergent hybrid modeling piece a little deeper. I know it's a kind of a mouthful and not many people maybe heard of it. But Solid Edge seamlessly combines traditional BREP solid models with triangular mesh models without time-consuming and error-prone conversions. So Solid Edge convergent modeling allows the traditional BREP operations of digitally scanned 3D data and models born out of this generative design, which reduces rework while supporting modern additive manufacturing processes for very complex shapes. Maybe this example here you see here. And also simulation studies can also be performed on these convergent hybrid models. So again, these are using this generative design and reverse engineering without the need to convert that to a BREP, such as models including the generative design optimization or an STL file and converted mesh models. So now we have the ability to analyze these hybrid models for various study types to verify our design that meets our requirements. So let's check out a quick video of this convergent hybrid modeling to get a better understanding of what it is.
Long, long ago, at the dawn of 3D CAD, two technologies emerged that allowed us to turn our creative thoughts into innovative products more easily. Facet modeling represented surfaces as connected planar triangles, and surfaces were positioned to represent 3D objects. It was favored for its simplicity and ease of coding, but engineering accuracy required very large data sets. Boundary representation, BREP, used mathematically defined surfaces connected by topology to represent objects as watertight volumes. This was concise and precise, but also more complex. BREP proved the best solution for engineering, and today, the vast majority of CAD/CAM systems for design, simulation, and manufacture of consumer and industrial products are BREP-based. Facet modeling developed as the preferred solution for less precise, high-speed shape representation, such as gaming, animation, and digital mock-up. Recently, facet data has become more common and more valuable in engineering workflows, with the emergence of high-precision, low-cost 3D scanning, medical scanning, and 3D printing. But the benefits of using facet data are reduced by the need for one-way, one-time conversion to BREP format, which is often time-consuming and error-prone for numerous technical reasons. The ideal, but extremely difficult technical solution is to fully integrate facet data representation into a BREP system's architecture, so facet data can be used for all operations without conversion, as if it is BREP data. Siemens PLM has developed this groundbreaking solution and calls it convergent modeling. Use facet data in your BREP workflows with no data conversion and all the benefits of both technologies. Take a look into convergent modeling and take your innovation to a whole new level.
Okay. So again, Solid Edge continues to focus efforts on improving technology for this reverse engineering design, and we see it every year or so. So giving us the ability for AI-generated generative design functionality, also referred to as topology optimization. So this functionality allows the software and its algorithms to generate hundreds of designs based on some very basic input or parameters that need to be maintained. And in minutes, not hours or days, several algorithmic design options are available for the user to review and determine kind of which generative design concept works best for their project. So here you can see kind of a comparison of what a designer's brain methodology looks like today when designing a part. You know, very kind of crude, straight-edged, a lot of right angles. And then on the right-hand side, you see a generative design example. So again, with just some basic parameters, it's able to kind of generate this organic looking shape that most designers that I know of today wouldn't really come up with on their own. So this is a pretty good tool. And so based on your parameters, a specific component material, a design space, or an envelope, and permissible loads and constraints, Solid Edge will compute a reduced mass geometrical solution that maintains the structural integrity. So not only is this a smaller, lighter part, also has better airflow, and it also is a lot less weight, so a lot less material. So probably a cheaper part, and much easier to manufacture into 3D additive manufacturing. So again, parts resulting from generative designs inside of Solid Edge are ready for this additive manufacturing. So high resolution 3D printers can handle these complex shapes. So then shortening your production time to market or speeding the production of replacement parts. So let's go ahead and check out a quick demo of kind of the concept of the generative design.
Solid Edge continues to deliver innovation in product development with built-in generative design capabilities. This advanced topology optimization toolkit helps designers create lighter components, minimize manufacturing material waste, and create highly customized designs especially suited for high-resolution 3D printing. Generative design produces an organic, reduced-mass geometric solution for a specific material optimized within a defined space, accounting for permissible loads and constraints. You define the design space with keep-out areas and a target weight reduction, and the software automatically computes the geometric solution. This faceted or mesh model is immediately ready for additive manufacturing, where it could serve as a core for mold-based design. Further revision of this mesh model to prepare for traditional manufacturing is possible with Solid Edge 3D modeling commands. Reducing the weight of existing components is a snap with the suite of Solid Edge next-generation design technology. Siemens Convergent Modeling supports BREP modeling operations on facet bodies without conversion. You can build analytical features into the generative body, complete with dimensions and PMI. And as always, Siemens synchronous technology makes for fast and flexible modification. Shorten your time to market with a higher performing product while minimizing the costs associated with downstream material waste. Solid Edge, shaping the future of product development.
Okay. So Solid Edge, again, has some great, easy to use tools to help us kind of prep a model before we even bring it into Solid Edge. So kind of the first step when importing this mesh data from a scan, we have the opportunity to ensure that and set the import units are appropriately set. So here we can confirm whether they're inches or millimeters, or if maybe the scan came in inches, but we need millimeters, we can set that before we even open the model. And then once we have the model open, we've got a few steps that we kind of run through that are just your traditional tools. So a geometry inspector command. This will ensure that there aren't any issues or small entities needing repaired on the model. So this is a good thing to kind of, it may highlight an area that may cause problems down the design process, and you'll kind of know where that is. And you even have the ability to heal or correct some of the issues right here in this step. And then following that geometry inspector, it's also a good idea to run the optimize command on the body. So what this does is it increases the quality of the model by simplifying some of the B-spline definitions. It can also heal edges and identifies blend-like surfaces. So these are kind of just a couple of prep tools that are inside of Solid Edge that aren't really even in the reverse engineering tab just yet. Let's go ahead and look at that. So once we have this mesh inserted into Solid Edge, here's kind of an overview of what the general traditional reverse engineering process looks like inside of Solid Edge. So we first read in that STL or that scan file into Solid Edge. And then we head over to the reverse engineering specific tab where we have tools that can help us repair any undesirable mesh that may have been brought over from the scan. Then next we identify our regions. Then we extract our surfaces. And then once our surfaces are extracted, we can then use our surfacing tools to extend and trim our surfaces to give us our final design look, as you can see from that step 4 there. And then finally, we have a tool available to stitch these surfaces together, which can generate our solid body. So you kind of go through this workflow to go from a scanned mesh data all the way down to that solid B-rep model that you could then make changes to. So let's look at each one of these steps a little closer, kind of just identify and understand them a little better. So the first step is, again, that mesh repair. So as soon as we bring our model in, we may want to review it and kind of understand there are some, maybe this part is 15 years old and maybe there's some functionality or features on it that we just no longer need for our new product design. So here we can select to either delete or smooth or fill holes in any of the mesh that may be unwanted. So with the delete mesh command, we can delete any selected mesh or facet on the body. Usually leaves an open hole there. So then the next step would be to go through and smooth our mesh, which allows us to smoothen the mesh in an area to reduce the amount of imperfections during the scanning process. So maybe there was some blemishes or dirt or debris on the part that came through in the scan, but isn't actually part of the part. Here we can get rid of that and correct that. And then, like I said, when we delete some mesh, it kind of leaves us with an open hole there. So we have an open hole or a fill hole command. And this allows us to fill in any deleted features in an area that help us kind of solidify the body. And then finally, we have a remesh command. And this allows us to remesh our body to a specific mesh size. So we can give it a target size, a minimum size, and a cordial tolerance. And there are a few advanced remesh settings in here as well. So we can kind of control the minimum face quality as well as the surface growth rate. So again, that second step is the identify regions part. So once our mesh has been cleaned up and any unwanted mesh geometry has been removed, it's time to identify the different regions that will be moved over to the B-rep or CAD geometry. So this can be accomplished by using the Identify Regions toolset and offering options for both the automatic and manual method selections. So in most cases, I typically use a combination of both of these. Yeah, you can do an automatic, but again, the software is not 100% perfect. There's going to be some oddities that it may try to pick up as a flat surface, and maybe it's got a slight contour to it, and the system just quickly analyzes it as a flat surface. Kind of depends on the complexity of your part, but I like to use both. So I can use it automatic to kind of give me to speed up the time, and I can go through and analyze to make sure all of the surfaces are correct, or if they're not, and then I can use the second method, which is I'm sorry, the automatic method will place colors on the mesh. Let me explain the automatic method first. Um, this basically allows us to it adds colors to the surfaces based on the specific geometry types. So accuracy level can also range from either 1 to 10, 1 being the least accurate and 10 being the best. I like to usually do somewhere in the middle, especially if it's a very complex part. You may see some performance delays if you go with a 10. But again, you can kind of play around with these ranges to find what fits best to you. And then the manual option allows us to manually identify what types of geometry you wish to use on any of the mesh. So we can use this element in automatic selection. Maybe it misidentified a surface or geometry. So this is kind of where both of those automatic and manual selections kind of come into play. So then the next step is the extract surfaces. So once our regions have been identified, the next step is to extract them to make them BREP surfaces. So again, there are two methods to do this as well. We have an extract command, and then we have a fit command. So the extract command allows surfaces to be automatically created based on the regions highlighted in the last step that we just reviewed. And you can see from the color legend here, just by default, the color yellow is identified as a planar surface. The cyan color is identified as a cylindrical surface. Red is a spherical, blue is a conical, and pink is a B-spline, kind of a oddity area of the part. And then the fit command is pretty much the same concept, but it gives you a little bit more control. So the fit command will allow you to define exactly the type of surface you wish to create, no matter what color it is. So you can actually go through and select multiple mesh facets to include. So here we're selecting several of these small little entities to give us the flat surface that we're looking for, but the automatic method didn't pick up on. Then the next stage would be to edit and trim the surfaces. So once you've extracted all the desired surfaces that you need for the mesh, use the solid edge surfacing tools to trim, extend, split, or to modify as needed. And then here's the finished result. So on the left-hand side, you can see it's just a bunch of overlapping surfaces. And I will state that the overlapping surfaces are very important. This just kind of cuts down the trimming, the ease of the trimming process, and kind of makes it kind of verifies and solidifies that you have a nice seam at the corners where these two surfaces may meet. And on the right-hand side is, we spent a few minutes clipping away and trimming and extending all these surfaces. And now we've got our desired result, but it's still just a collection of sheet surfaces. So then that final step is to stitch the solid. It's to stitch to a solid model. So now that our model's been cleaned up, it's exactly what we need. It's time to stitch the surfaces together to create our design body. So the stitch command creates a construction body by basically stitching multiple sheets together to create a solid surface or a solid body. So to recap, we kind of walked through the general design process of reverse engineering, where we took the mesh data, identified usable regions, converted those to the surfaces, and then modified and trimmed those surfaces, and then finally converted that mesh to a solid construction body. So now we're ready to make any last minute changes use it to the model using the power of synchronous modeling technology. So, but this is the common workflow, but it's been greatly improved recently with the introduction and addition of the convergent hybrid modeling functionality that we covered earlier. So here we can see 5 common pillars or steps in that process. But with that new convergent modeling concept, we now have the ability to work directly on those mesh bodies in the hybrid approach. So we can use now common material adding and removing commands like extrude, revolve, hole, rib, network, and many more, as well as section views and section by plane. So this all pretty much eliminates 4 of those 5 steps in the previous workflow that we just reviewed. So talk about process improvement. That's the epitome of the term. So in overall summary, we kind of looked at the what and the why of reverse engineering. And then we looked at some common reverse engineering workflows inside of Solid Edge. We looked at how we can easily manipulate the mesh data, and then reverse engineering specific tools that are built inside of Solid Edge and that continue to grow and be enhanced. And then we looked at this new convergent hybrid modeling workflow process improvement. So from here, we'll take any questions that you guys may have. Misty, I'll open it up to you to see if there's any questions that may have popped through the chat.
All right, thank you, Aaron. So guys, I'm going to go ahead and take everyone off mute. All right, there you go. Yes, we do have one question that came through, and it says, what is the versions of Solid Edge that includes reverse engineering tools?
Great question. So the reverse engineering specific tab or the environment, as well as the 3D print specific tab, they come included inside of Solid Edge in versions Solid Edge 2020 and up, and they are in both the classic and the premium seats of Solid Edge. So if a company has a combination of both classic and premium seats, those are included in the software, so no additional cost for that specific functionality. I think the only versions that aren't included in are the free drafting and design environment, and then the foundation, the seat foundation license.
All right, thank you. We'll give it a moment, see if anything comes through. Okay, Aaron, here's another question. Can you 3D print directly from Solid Edge?
Another great question. Yeah, so as I mentioned, there is a 3D print tab inside of the Solid Edge environment, and in there are a lot of different functionality and tools and prep tools. But yeah, you can send a file, whether that be a mesh or a BREP model, directly out as either a 3MF file or an STL file that can be pretty much absorbed by any 3D printer.
All right, here is another question, and this is kind of a part A and a part B. So is generative design included with Solid Edge, and is there an advanced generative design module?
Yeah, so the generative design is another module along with the 3D print and the reverse engineering that is included in the classic and premium seats of Solid Edge, and it's just kind of the basic generative design tool. But there is an add-on portfolio product that kind of supplies a little bit more advanced features, additional software, and computing power. So if you needed to take that convergent modeling or generative design to the next level, there is another level above what's included in the Solid Edge Classic and Premium seats. So yeah, most of the stuff we're showing here is pretty much free to those that have the Classic and Ups Solid Edge.
Excellent, thank you.
Yeah.
All right, so we're going to give it about 1 more minute. If anyone else has any other questions, please feel free to take yourself on mute and ask the question live, or you can enter it into the chat, whichever makes you happy.
And you can always screenshot the contact information on the slide here. So if you come up with a question an hour from now, or you go to lunch and come back and have a question you wish you asked, you can just send it to my email address directly.
Thank you, Erin. That's very nice.